When we look at simplifying radicals, we start with looking at what a radical is. A radical is going to be a term that has a radicand inside the radical symbol, and then this term here is what we determine as the index. Now, you've probably seen them before when dealing with square roots. All square roots have an index of 2, but we just don't write the index value actually there. So if I look at the square root of 1 equals 1, square root of 4 equals 2, square root of such things like 169 is 13, and we go down through there, and probably a lot of these you have memorized. And these are the number, or the perfect square, is the value you'd get when you square another value. So if I squared 14, 14 times 14 gives me 196. Conversely, I can do the square root of 196 to get to 14. Now we're also going to go a little bit higher and look at cube roots, and this is when you look at what value would you cube to get to these numbers. For example, 2 times 2 times 2 is 8. So we'd say the cube root of 8 is 2. The cube root of 125 is 5 because it's 5 to the third. We can go on higher with higher indices and get different roots, 4th root, 5th root, 6th root, and allow us to simplify. So what we're looking for whenever we simplify radicals is we want to be able to break this up so we can pull out perfect squares, cube roots, or these sets of numbers that simplify the radical down. So if I have a number for the letter A here, and these different terms are all factors of A, I want to find n of them to allow to factor out. Now that's a very abstract way to look at it, so let's look at a couple basic examples before we go further. So for example, the square root of 8, if we look at the factors, is 2 times 2 times 2. I need to find, because it's a square root, a set of two numbers that are the same in order to take it out of the radical. Well, I happen to have two 2's here. So if I take out the 2's, I can rewrite this as 2 root 2. The other way we could have represented 8 is such as saying 4 times 2, which 2 times 2 is 4. This is by looking at perfect squares. The square root of 4 is 2, taking it outside the radical, and the 2, which is by itself, stays inside the radical. If we keep going and look at the square root of 20, the square root of 20 is 5 times 4. 4 is a perfect square, so the square root of that is 2, which means the 2 comes out, and the 5, which doesn't pair up with anything, nor is a perfect square, does not come out. 72, we could say the square root of 36 times 2. 36 is the largest perfect square factor that it has. The square root of 36 is 6, which makes it 6 root 2. So let's say we took 72, and instead we write the square root of 9 times 8. Now 9 we know is, square root of 9 is 3, so that becomes 3 root 8. Now that's not the same as 6 root 2, but we know it should be the same thing. But we can look back up to and say, well, the square root of 8 turned out to be 2 root 2 because there's a pair of 2's in there. So this actually goes 3 times 2 root 2, which when we put together still gets to 6 root 2. So it doesn't matter necessarily even if we look for factors. You still have to look for perfect squares, you still have to look for pairs, but even if we don't get the largest perfect square, we can still use those factors to get to that process. Now, what if it suddenly became the cube root? So before we were looking for sets of 2, now we're just looking for sets of 3. So for example, 96, if we look at all of its prime factors, it's 5 2's and a 3. So if I look at sets of 3, I got 1 there. That only has 2, that's not coming out, and that's just 1, that's not coming out. So that one set of 2 comes out, and then it's going to be the cube root of whatever's left over. 2 times 2 times 3 is 12. So we can even extend that idea to whatever root that we have, 3rd root, 5th root, 7th root, whatever we go to. So what now about if we have variables involved? So I'm going to go with this three separate parts. I have the square root of 80, x to the 3rd, and y to the 6th. Let's start with the square root of 80. Square root of 80 is 8 times 10. I can break apart the 10 into 5 and 2. 8 is going to be 2 and 4, and then some 2's off of the 4. So I have 2 sets of 2. They come out to become a 4 on the outside. 2 times 2 gives me 4. The 5 is left, so it's 4 root 5. So if by itself it was just the square root of 80, we would say it's 4 root 5. X to the 3rd. X to the 3rd means I have 3 x's. that means I have one set. So the x comes out, and there's one x left over. Y to the 6th means I have 6 y's. If I look at sets of 2, that means I have y to the 3rd with none left over, so I don't need to write it. But let's go back to that for a second. We said this was square root. Let's throw a 2 in there. We don't need to write it, but let's just keep it there for a second. If I did 3 divided by 2, it would give me 1 with a remainder of 1. So if 3 divided by 2 gives me 1 set with 1 left over. 6 divided by 2 gives me 3, which is 3 on the outside, and then the remainder, if I had any, would go on the inside. I don't in this case. So what our answer turns out to be is I have 4x and y to the 3rd on the outside, and on the inside it's 5x. So now we take that and look at the cube root of 216 first. Then we got cube root of x to the 12th, cube root of x to the 7th, and then the cube root of z squared. 216 is 6 times 36, and 36 is 6 times 6. From that, I see that I have 3 6's, and this is a 6. If you missed that, or you factored it differently, you would also get to 2 times 2 times 2, 3 times 3 times 3, which would give you a 2 and a 3, which also gets you to 6. So however you factor it, you need to get that the cube root of 216 is 6. That part's done. Throw a 6 over there. 12 and 3. So I have in 12 4 sets of 3. Or 12 divided by 3 is 4. So that's going to be x to the 4th. No radical there, so that goes on the outside. That's not x, that should be y. So y to the 7th, and that's inside the cube root. 7 divided by 3 is 2, so that means I have 2 sets that come out. The remainder is 1, so that's 1y left inside. So I'll write y squared, and then cube root of y there. Z squared in the cube root. I have 2 z's. I need 3 to come out. It's not going anywhere. It's not going to simplify, so we just leave it as that, and the z squared stays inside. And this turns out to be our simplified expression. So let's keep going. So now in the next one, the square root of 320m to the 10th with a 5 on the outside. The 5 is just a number to multiply by. It's a coefficient out in front. If I have any numbers on the outside, I'll multiply by that. But let's start at 320. 320 is 5 times 64. 64 is 8 times 8. So I'm going to take out a set of 8s. So bringing down the 5, bring out a set of 8. The 5 here stays in the radical. So that takes care of my coefficients, my numbers. M to the 10th in the square root, 10 divided by 2, like if I had a 2 here, would give me 5. Or I could say that in 10 there is 5 sets of 2. So m to the 5th comes out. Putting this together, I get 40 m to the 5th square root 5. Next, for the 4th root of 144x to the 6th. 144 is 12 times 12. When I have 3 and 4, 3 and 4. And get down to the 2's. From that, I see that I have a set of 2's. I have 4 2's there because it is 4th root. So that's going to come out. And then the 3's, oops, it's 4th root. The 3's are going to stay inside, but I'm not going to write 3 squared. I'm going to write 9 instead. Just multiply them together. Now for x to the 6th. X to the 6th has 1 set of 4's in it. So that x comes out. When I take those 4 away in the set, it leaves me with 2 left over. So that's going to be 2x, 4th root of 9x squared. For our next one, 6w times 400. 400 is actually a perfect square. It's 20 times 20. So we get 6w times 20, which is 120w. The cube root of 40d to the 8th. 40 is 8 times 5. Now why I'm picking that one is I know that 8 is a perfect cube. It's going to have 2 and 4, which gives me 2 and 2. So the 2's are going to come out. 2 on the outside. The 5 stays on the inside. Now I just need to simplify the exponent for d. d to the 8th, if I'm looking at sets of 3, I have 2 times 3 is 6, so that takes out 2 sets, so that's d squared on the outside. The remainder then would be 2, so that's d squared. 96, we looked at the factors earlier, and that was 5 2s and a 3. So since we're now looking at the 5th root, actually this whole set of 5s come out, or 2s come out, and the 3 stays inside. For f to the 22, if I divide 22 by 5, it goes in 4 times plus a little bit more. So I'm going to take out an f to the 4th. The remainder, or the remaining amount, is just 2 of them, so we'll write f squared. 2f to the 4th, 5th root of 3f squared. The last one, 1024 p to the 10th inside the 8th root. So we got 2 times 5, 12, 2 times 2, 56, 2 times 128, 2 times 64, 2 times 32, 2 times 16, 2 times 8, 2 times 4, and then 2 and 2. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is actually the 8th root of 2 to the 10th, p to the 10th. So 2 to the 10th has one set of 8 2s. So that comes out, and that leaves me with 2 on the inside. P to the 10th also has one set, so that comes out and leaves me with 2 on the inside. Now when I put this together, I'm going to go 2p, 8th root of 4p squared.